Hi everyone, welcome back to Math 251. Today's mathematician of the day is Martha Euphemia Lofton Hayes, who was the first Black woman to receive a PhD in mathematics in 1943. From there, she went on to chair the Washington, D.C. School Board and created a more inclusive math curriculum for their students. What an awesome person. And did you know that the English word for sine, like the math function, comes from a series of mistranslations of the Sanskrit word ja arda, which means chord half. We are not good at translating things, are we? All right, so we have been learning lots about derivatives, and today we are continuing that. We're going to be talking about the derivatives of inverse trigonometric functions. If I were to list out the derivatives of trigonometric functions, inverse trigonometric functions, you'd be like, what the heck, Amanda? Where do these come from? So I'm going to show you where some of these come from. So how do we get the derivative of sine inverse of x? Well, if I have the sine inverse of x, if I say that this is equal to y, remember, sine inverse of x means that sine of y equals x. This is how x and y are related to each other. So if I took the derivative of both sides of this, with respect to x, well, I'd have to use implicit differentiation here. So if I used implicit differentiation, my outer function would be sine of x. My inner function would be y. That means f prime would be cosine of x, and g prime would be y prime. So I would get f prime of g times g prime is equal to the derivative of x, which is just equal to 1. So then solving for y prime would give me y prime equals 1 over cosine of y. Well, that's great, but what is cosine of y here? Well, I want to write it in terms of x instead, because my sine inverse of x is in terms of x, not in terms of y. So I want to get this in terms of x. I have the identity cosine squared of any angle plus sine squared of any angle is equal to 1. Well, this means that cosine squared of y is equal to 1 minus sine squared of y. And this gives me that cosine y, if I take the square root of both sides here, cosine of y is equal to plus or minus the square root of 1 minus sine squared y. But hold on, I know what sine of y is. According to here, sine of y is equal to x. So this is plus or minus the square root of 1 minus x squared, since I know that sine of y is equal to x. So plugging this back in to this equation here gives me 1 over square root of 1 minus x squared. We only include the positive version since I can't do this implicitly, so I only include the positive strand. I don't expect you to know how to do this for any other trig function. In fact, I don't even expect you to know how to do it for this one. I just thought I would show you where this comes from, because what we just showed is that the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared, which seems a little bit disconnected. So I just wanted to show you where this comes from. So the derivative of sine inverse, as we just showed, the derivative of sine inverse of x is equal to 1 over square root 1 minus x squared for x between positive 1 and negative 1. Remember, with sine with sine inverse, cosine inverse, all of the inverse trigonometric functions, our domain is pretty restricted. All right, so let's use this to compute the derivative of sine inverse of x squared minus 3 and tangent of sine inverse of x. So on both of these, I am going to have to use the chain rule. So here on the first one, I want to find the derivative of sine inverse of x squared minus 3. So I'm going to have to use the chain rule here, since I have a function, x squared minus 3, inside another function, sine inverse of x. So my outer function here is sine inverse of x, and my inner function is x squared minus 3. That makes f prime, according to my theorem up here, the derivative of sine inverse of x is 1 over square root 1 minus x squared. And g prime is equal to 2x. So now using the chain rule, I take f prime of g times g prime. This is equal to 1 over square root 1 minus, except instead of that x squared, I plug in a g. So that's x squared minus 3 squared times g prime. That's 2x. So if I simplify this a little bit, I get 2x over square root 1 minus, if I square out x squared minus 3, I get x to the power of 4 minus 6x squared plus 9. And if I distribute that negative and combine like terms, I get 2x over square root negative x to the power of 4 plus 6x squared minus 8. And that is the derivative. So I had to use the chain rule, treating my outer function as sine inverse of x and the inner function as x squared minus 3. And then from there, I just plugged it all in and simplified it. Next, I want to find the derivative of tangent of sine inverse of x. Tangent. Don't you just love trig? I do. All right, so again, here we're going to have to use the chain rule, since I have a function, sine inverse of x, inside another function, tangent. So my outer function is tangent x, and my inner function is sine inverse of x. That makes f prime equal to, the derivative of tangent x is secant squared of x. Whoops, I didn't mean to write that prime. This is just g is equal to sine inverse of x. And then g prime is equal to 1 over square root 1 minus x squared. So then f prime of g times g prime is equal to secant squared of sine inverse of x times g prime. So that's times 1 over square root 1 minus x squared. So simplifying this, bringing that 1 square root 1 minus x squared to the bottom just gives me secant squared of sine inverse of x divided by square root 1 minus x squared. That is our derivative here. Pretty cool, yeah? So this one involves a lot of trig functions. I do think it's worth noting that in this second example we have trig functions left in our answer, and in this first example we did not have any trig functions left in our answer, even though we had a trig function originally. So that is definitely worth noting. All right, so now we are going to learn all of the derivatives of the inverse trig functions. I would say only a few of these you should really learn and memorize. The others are not super important. So I would say, yeah, anyway, let's write them down and then we'll discuss that. So the derivative, as we've already seen, of sine inverse of x is equal to 1 over square root 1 minus x squared. The derivative of cosine inverse of x is equal to negative 1 over square root 1 minus x squared. For both of these, this holds for x strictly between negative 1 and positive 1. Okay, the derivative of tangent inverse of x is equal to 1 over 1 plus x squared. And the derivative of cotangent inverse of x is equal to negative 1 over 1 plus x squared. These two are both true for all x, so x between negative infinity and positive infinity. And finally, the derivative of secant inverse of x is equal to 1 over the absolute value of x times x squared minus 1. And the derivative of cosecant inverse x is equal to negative 1 over absolute value of x times square root x squared minus 1. And both of these are true for when the absolute value of x is greater than 1. So these look a little bit strange for trig functions, right? So that's why I did that very first example showing where the derivative of sine inverse of x comes from. So that's why we have all of these like x squareds, square roots, stuff like that. I would say here that the most important ones for us to know are sine inverse, tangent inverse, and cosine inverse. The other three we don't see a lot out in the wild, so to speak. So I would say focus on those three. All right, let's do another example. Example 2, evaluate f prime of 2 square root 3, where f of x is equal to tangent inverse of x divided by 2. So I first need to find the derivative of tangent inverse of x divided by 2, right? So in order to do this problem, the derivative of x times tangent inverse x minus 2, I'm going to have to use the product rule, since I have the product of two functions. And then we have a chain rule inside there. But first let's look at the product rule. So I'm going to call f equal to x and g equal to tangent inverse x over 2. That means that f prime is equal to 1. And to find g prime, since I have a function, x over 2, inside another function, tangent inverse x, I'm going to have to use the chain rule here. So here I'm going to call my outer function h. So my h is equal to tangent inverse of x, and my inner function j is x over 2. That means that h prime is equal to the derivative of tangent inverse x, if we look at the table up above, is 1 over 1 plus x squared. And j prime is equal to 1/2. Okay, so now plugging into the chain rule gives us g prime is equal to h of j prime, so that is, h prime of j, sorry, Got my variables mixed up there. So h prime of j is 1 over 1 plus x over 2 squared times j prime, which is 1/2. So if I were to expand this a little bit, I would get 1 over 1 plus x squared divided by 4 times 1/2. I don't like that fraction over 4 on the bottom, so I'm going to multiply this whole thing by 4 over 4. And that will give me 4 over 8, multiplying this 2 with this 4, plus 2x squared, since I have that 2 there as well. All right, so this is my g prime. So now I have f, f prime, g, and g prime, and now I can plug into the product rule. So the product rule says that I take the first, that's x, times the derivative of the second, which is 4 over 8 plus 2x squared, plus the second tangent inverse of x over 2 times the derivative of the first. So this is our derivative, x times 4 over 8 plus 2x squared plus tangent inverse of x over 2. And if I were to plug in the point x equals 2 square root of 3, so at x equals 2 square root of 3, I get the derivative, sorry I'm running out of room here, is equal to, let's see, I would get 8 square root of 3 on the top here over 8 plus 24 plus tangent inverse of square root of 3. And this would give me, if I simplified this, square root of 3 over 4 plus pi over 3. So here we had to use the product rule and the chain rule all in one, and then we plugged in a point. If you don't know what it means to take the tangent inverse of square root of 3, I would maybe review your unit circle a little bit. Alright, I'd like for you to pause this real quick and try example 3 on your own. Find an equation of the line tangent to the graph of g of x equals secant inverse of 2x at the point 1 comma pi over 3. So go ahead and give this one a try. Alright, hopefully you've tried this on your own. So I want to find the derivative of secant y equals secant inverse of 2x. I want to find the line tangent at a certain point. So I need to use the chain rule here. So using the chain rule, I get my outer function is equal to secant inverse of x, and my inner function is equal to 2x. That means f prime is equal to the derivative of secant inverse x is 1 over absolute value of x times x squared minus 1. And I get g prime equals 2. So then, f prime of g times g prime, using the chain rule here, is 1 over absolute value 2x times quantity 2x squared minus 1, that's f prime of g, times g prime. This simplifies to 2 over absolute value 2x times square root 4x squared minus 1. So this is our derivative here. And I want to find the tangent line at the point 1 comma pi over 3. So I first need to find the slope by plugging in my x value into this derivative. So at x equals 1, I get 2 over absolute value of 2 times 4 minus 1. This simplifies to 1 over square root of 3. So this is my slope, or my m value. And then if I want to solve for the tangent line, I need to plug into y equals mx plus b. My y value here is pi over 3. My slope I just found to be 1 over square root of 3. My x value is 1. So I get that b is equal to pi over 3 minus 1 over square root of 3. So the tangent line here is y equals 1 over square root of 3, square root of 3. Y equals 1 over square root of 3x, I keep writing that, square root of 3 times x plus pi over 3 minus 1 over root 3. That is our tangent line. So here we had to use the chain rule to find the derivative of secant inverse of 2x. And then from there I plugged in my x value to find the slope of the tangent line at a certain point. And then I plugged into y equals mx plus b to find the y-intercept. Alright, so we have been talking so far about inverse trigonometric functions, but we can also take derivatives of inverse functions in general. So that is what the next two examples will be over. How do we find the derivatives of inverse functions in general? So we want to consider the general linear function f of x equals mx plus b, where m is non-zero. We first want to write the inverse form of this function, so I want to solve for y, basically. So I have the function y equals mx plus b, and I want to solve for y. That's the inverse. Oh, excuse me, solve for x. That's the inverse. Solve for x. So if I subtract mx from, actually let's subtract b from both sides. So I'm trying to solve for x. So I get y minus b is equal to mx. And then isolating x, I will divide m by both sides to get x equals y minus b over m. So that is the inverse function here. And then I know that here, if y is f inverse of x, so if y and x are inverses of each other, this means that f of y is equal to x. This is just the definition of the inverse here. So if I swap the x and the y in the inverse that I just found, I'll get y is equal to x minus b over m, swapping that x and the y there. All right. Now I want to find the derivative of this inverse function. So how do I find the derivative of this? So I have the function y equals x over m minus b over m. I can split those into two parts since my denominator is the same. So if I were to find y prime of this, well, remember that b and m are simply constants. So this b over m term will simply disappear when I take the derivative, and I will just be left with 1 over m as my derivative. So the derivative of the inverse function is the reciprocal of the slope. We're not actually going to do part C. Instead, let's just write down what we learned in part B. So note that the derivative of the inverse, that's what we found in part B, the derivative of the inverse is the reciprocal of the derivative of the function, right? Because if I look at our function, y equals mx plus b, what's the derivative of that? Well, the derivative of that is just equal to m. So the derivative of the inverse is simply the reciprocal of the derivative of the function, right? We found that the derivative of the inverse was 1 over m. That's the reciprocal of the derivative of the function, which is m. You might have to read that a couple times in order for it to make sense, but that is certainly true. So next we have a theorem. Let f be differentiable and have an inverse function on the interval I. If x naught is a point of this interval at which the derivative at that point is non-zero, then f inverse is differentiable at y naught equals f of x naught, and we have f inverse prime at y naught is equal to 1 over f prime of x naught, where y naught is equal to f of x naught. So we have to be pretty careful here because I'm trying to find this equation is only valid for if I'm taking the f inverse prime of y naught. So I have to be very careful with my relationship here between x naught and y naught. So let's use a table here to calculate f inverse prime of 5 and f inverse prime of 1. So if I want to take f inverse prime of 5, that's all good and dandy, but I need to see this 5, which x value does this 5 relate to, right? I need to solve for this x value, x naught, in my equation here. So I get here 5 is equal to y naught. So which x gives us an output of 5? Well, I look at my table and I see that the x value 1 gives me an output of 5. So I get that f of 1 is equal to 5. So when I plug in, so f inverse prime of 5 is equal to 1 over f prime of 1, since my x value that corresponds to my y value here is 1. So I look at where f prime of 1 is, and I see that f prime of 1 is equal to 3 halves. So this is 1 over 3 halves, which is equal to 2/3. Again, we have to be very careful with our x's and our y's here. We basically first have to see which input my y value corresponds to, and then from there I see what the derivative of that x value is. Okay, and then I also want to solve for f inverse prime of 1. So here, this 1 is my y naught. So I need to say which x value gives an output of 5. Excuse me, 1. So I look at my table and I see that none of my f of x's is equal to 1. And because of that, this makes f inverse prime of 1 undefined. because we don't have an x value such that f of x is equal to 1. All right, that is it for today. We certainly did learn a lot, didn't we? I hope you feel comfortable with this. If not, I encourage you to come to the Zoom sessions and ask questions. Hopefully, I'll see you there.